So, we are taking up another topic called the high bulk yarn. We have learned something about the bulk yarn. This is slightly different connotation and the process also is slightly different. So, last time when we met we had talked about bulk continuous filament yarn and the jet was there, the function of the jet, why the yarns, the bulk yarns, the BCF yarns are more resilient compared to stuffer box, why the filaments do not get entangled, what are the likely application of such type of a material, and it is possible with this technology to do a true spin draw texturing process, which no other texturing process can claim. So, what next? The yarn which was a BCF yarn was it a bulk yarn? Was it a bulk yarn? Right. But it is not bulk yarn because it is close to modified stretch yarn. Because what were you doing in the BCF? You had individual filaments being crimped and then you could stretch, it will stretch and recover. So, although the name says bulked continuous filament yarn, so bulk has increased, but it is not a bulked yarn. Your air jet texturing or air jet textured yarn, that was a bulked yarn. So, what we are now looking at possibly another method with which we can actually produce a bulk yarn, right. So, that is what we call as a high bulk. The bulk is high, that is how the name has come. Certainly higher than, if you look at percentage bulk terms, would be generally higher than air jet also, you know. But the name has stuck, this is a high bulk yarn. So, this yarn which we will call a high bulk yarn would have a typical stress strain characteristics of this type. Which means there is no stretch. That means it qualifies for bulk yarn. So, this is an important part. So, we are looking at another method of producing a bulk yarn. So, the principle that it uses to produce is called the differential shrinkage. That means there are two components in the yarn, one shrinks, the other does not. One component shrinks and other does not. So, if this happens, you get bulk. We will see. This type of a material, do we call it a biconstituent yarn or a bicomponent yarn? So, there are two materials in this yarn, one shrinks, the other does not shrink. So, what do we call this yarn? A bicomponent, you have heard of the term bicomponent, which can also produce bulk in different ways. But that bicomponent and biconstituents have to be differentiated. A bicomponent yarn is a single yarn with two different polymers. Extruded together then because of their differential properties, response to a thermal or a hydrothermal or any other input that you have, they may respond differently. And so, a biconstituent yarn on the other hand has got two components which are individual. Let us say two fibers, A and B, spun together. Spun together, component A, component B, blend them, make a yarn. So, they are two individual components. So, this kind of a material we like to call as a biconstituent yarn as against bicomponent. So, what do we need? We need a shrinkable component and a non-shrinkable component. When we say shrinkable, you know all thermoplastic materials shrink when you heat them. And a simple test that you can perform, take the fiber near the flame, not inside the flame, and you can see the fiber shrinking away. That is the characteristic of a thermoplastic material. So, in that sense every fiber would shrink, but that is what we do not mean. When we talk about shrinkable with some input, thermal or otherwise, it would shrink to something like 25 to 30% of its length. And when we talk about non-shrinkable, this may also shrink a bit, but that is 1 to 2%. So, there is a differential part of it. So, one component shrinks quite a lot, other shrinks less. So, differential must be high. So, theoretically if somebody says non-shrinkable, what is the non-shrinkable component? Well, the one which shrinks very less, instead of calling it zero shrinkage, or non-word absolutely may not be the best word to use, but that is how people have been using it. Very, very low shrinkage is what we call a non-shrinkable component. The one which shrinks quite high is the one, and difference between the two should be high. And should be high means the difference should be close to 25% or more. If the difference is 3%, 4%, you will get some effect, but that is not going to do. That means whatever is called a shrinkable component is a special fiber, in that sense that you have to work on this, or selection. If you can do that, then it is possible. Now, there are two different types of fibers. So, how do we make a yarn? So, it is approximately clear, it is going to be a spun yarn. So, till now we had been handling filament yarn, whether it is a false twist, BCF, air jet, entanglement, we were talking about filament yarn. Now, this particular thing is a spun yarn. So, you have staple fibers, two components, you mix them up, make a spun yarn. So, this is different in that sense. Can the air jet and false twist texturing of spun yarns be done? Can the air jet texturing of false twist type of a thing or with spun yarns, can they be textured? We are just saying yes or no. Yes? All right. So, they can be. Process will be different, they can be done, but commercially of course, we are not doing so much of it, but it can be done. Air jet can be done, false twist also can be done. We will learn something maybe later. So, how does this work? If you say it is a spun yarn, how does it work? So, let us say there are two components, same staple length to begin with, you mix them, and after doing, we expect something like this to happen. If there is interaction between the fibers, after all, whenever you make a spun yarn, there will be interfiber friction. So, if one fiber does something, the other has to follow, they have to do something, respond to it. If they are lying very separately, then it may not respond. So, if you give a stimulus, so let us say the red yarn here fiber does not shrink, the black one shrinks in length. So, how will the non-shrinkable component respond? It will have to crimp, it have to buckle, it have to make some loops if you are intimate approximately. Then in the case of a spun yarn, you might just see the yarn before the bulk generation looked a mix of black and red. At the end of bulking process, the yarn may appear more red, because it is a non-shrinkable component, it has made loops, it is the one which is bending, it has come out and makes the sheath of the yarn, while the shrinkable component shrinks and goes more or less to the core. So, this is your differential shrinkage. The shrinkable component goes into the core. So, it is clear that you got to have shrinkable and non-shrinkable component. If you clearly look at the shrinkable component is shrunk, but does not really contribute much to the bulk. So, the combination is a bulk yarn. The bulk is being contributed by the non-shrinkable component, which wants to buckle, bend, make loops. So, that is one as the principle is concerned. So, what kind of an example possible? So, there is a yarn which is available in the market, which we call as based on acrylic fibers, but you can have blends, polypropylene jute. Now, how does polypropylene and jute would work? Are we saying polypropylene will shrink and jute will not? That can also happen, but then polypropylene must shrink more, but normal polypropylene may not shrink that much. On the other hand, what people have found is that if you treat wool in alkaline solutions of good strength, they shrink and crimp. And that process sometimes is known as the woolenization of jute. Like wool is a crimped fiber, a normal jute fiber for example is very straight, and by this alkaline treatment, because of shrinkages of components and swelling somewhere, not swelling somewhere, it becomes a crimped kind of a thing and bulk generates. But that is not the one. That means that this fellow can shrink in an alkaline solution, but polypropylene will not. So, one can always make systems where the one component which you want it to go to the core obviously must shrink, the one which you think abrasion resistance etc., should be high may come on the surface. So, you can create sheath core effect. But the commercial situation is this, that acrylic high bulk yarns are available. Lot of research here and there people do, and very innovative work also have been done. So, we concentrate on high bulk acrylic yarn. So, this is a product which is commercially successful, and so much so that as far as knitting yarn is concerned, hand knitting particularly, live bulk, wherever wool was there, you have acrylic. So, this is so much popular that it has replaced wool, and obviously people will love it if it gives the same kind of a characteristic and is obviously cheaper than wool, relatively easier to handle, do not have to dry clean, and if you remember, acrylic fibers are dyed with cationic dyes. The shades are bright and brilliant, which invariably woolen are slightly duller, very bright woolen systems you do not get it. You believe that it has to be handled differently. The dyes also are slightly different, one is cationic, the other is anionic, and so overall is there. But wool is wool, we do not say that we replace wool, one should not be thinking about it, but it has actually commercially done it. Price is very low, care does not have to be done too much. So, high bulk acrylic yarns are available anywhere you go in the market. The winter has started, you can go and see. It is all high bulk acrylic. Why is that the high bulk acrylic is there, and why not high bulk polyester, polypropylene, nylon are available? Principle we understand. So, what is so great about it? So, there is no product which is commercially available, we call high bulk polyester. Textured yarn is there, Falstress is there, Airjet is there, BCF is there, but no high bulk polyester, etc. commercially. So, they are not success. Somebody can try, once I know the principle, I will try. It is like, for example, you will not see a false twist acrylic filament yarn. So, you said, well, there is some problem with this, The problem was that if you heat it up, take it to a different state, it gets yellow, degradation can start. So, you do not want to get it, so let us keep that out. But this was one application which was as if meant only for acrylic fibers. And the reason is, you should be able to produce both shrinkable and non-shrinkable acrylics, which you can do, and we have not been able to do with polyester or nylon or polypropylene, although attempts have been done. So, the question that remains is why you couldn't do it. So, you should be able to answer this question like this: why does a fiber shrink? Because you need something to shrink. Let us say at the moment, just to simplify things, we are looking at thermal stimulus. The shrinkage can happen because of any other stimulus. So, we are looking at thermal shrinkage. Why does the fiber shrink? Clear? No. We agree that shrinks. Why does it shrink? Shrinkage means what? Disorientation. Or let us say molecular disorientation. So, if any change is taking place, this general equation must be satisfied. So, what does happen during this so called shrinkage in this equation term? The molecules are disorienting, which means delta S is increasing, which is a natural process, right. So, shrinkage will occur in a polymeric system like a fiber, but we have seen the same material can crystallize also. But now we talk about orientation, but if given a chance, it would like to go into a spaghetti shape. So, one of the reason of disorientation is it must have been oriented before. If you are oriented, only then can disorient. If something is already disoriented, you can't disorient more. So, what you are saying is an oriented structure will disorient easily. So, you create an oriented structure. So, that is what we do. All synthetic fibers after spinning are drawn. So, you are creating an oriented structure. Therefore, this material must shrink. Why the normal material does not shrink? Shrink to the extent that we want. You see, when you are stretching, if a molecule has been stretched, let us say it is a simple molecule also, and you stretch, it is not the crimped yarn I am talking about, the molecule. What is it? The carbon, carbon, carbon. So, you have a bond angle, which is in a natural state must be fixed. But if you do anything like a pull, this angle may not be exactly same, may not be. Otherwise, how does it matter whether this material is lying like this, if it is satisfied, or it is lying like this? How does it matter? It matters because by pulling you are straightening, and hopefully you have also stretched the angles, just like a spring which has been slightly extended, and you want to give a chance, it wants to come back. If you do not give this opportunity, it cannot come back. So, now we like to say it shrinks because there is oriented. So, it can go to a disoriented state, but when you give any input like thermal input, it should be enough to give freedom to this molecule to do what it wants to do. So, if someone says, so why polyester cannot do that? Oriented. That is because of this. That is, during this process of drawing, heat setting, etc., you are doing crystallization also. You have seen crystallization. If crystallization occurred, that is also favorable. That means also stable state. So, if the materials which we are talking about have a tendency to crystallize as well, then you are making maybe oriented, but also a stable structure. Oriented, stress induced crystallization, thermally induced crystallization. If all those things happen, then you are making material stable. And stable to what? Dimension stable means it is not going to shrink. So, your polyesters, polypropylenes, nylons, the moment you give these kind of inputs, they crystallize also, right. Polypropylene crystallizes while it is going spun from melt to solid. Nylons do at a certain rate and polyester maybe at a very slow rate, but they do crystallize. We were happy with that. We could do texturizing, but and we were happy that it will not shrink further. So, that is good part of it. So, the acrylic fibers have not behaved exactly the same way as the other thermoplastic fibers that we are talking about. It is possible to orient the fiber without it being crystallized. You have seen the polypropylene, the textile grade polypropylene, right. If it is isotectic, then you have a fiber, same molecular weight. If it is atectic, you have no fiber. That means, for crystallization also you need a certain facilitation. So, there is the methyl group which was a polypropylene coming out, it is on this side, that side, random or well governed. If it was well governed, it is called the isotectic. Acrylic fibers also have a nitrile group, which is the one something like that. Now, I have drawn everything on the same side. Why should it be on the same side? So, tacticity of the polymer that has been synthesized would determine whether it is going to crystallize very well or crystallize less. So, Ziegler, Natta, etc. were used catalysts to make polypropylene isotectic. Something similar has not been done here. So, by additional polymerization of type, you make things measure tacticity. So, what has happened is that actually the acrylic does not crystallize the way other fibers are doing. It is like a metastable state. It gets into a metastable state and slightly work very hard, it would crystallize also, but not sharp crystals, not various structures, alpha, beta, gamma stuff, because it does not happen. But what can happen is, when you orient this material, it may not have crystallized. For crystal, you have to come very close, but you can make various other kinds of van der Waals interactions, polar interactions, even if you are a little far. Cyanide nitrile group is a very highly polar group, and so because it is polar, so polar interactions can take place, and it is an abundance. Every second carbon you see this, right. Another molecule from the other side is coming, and they say suddenly a polar bond is created. You have done something, let us say you have drawn, you have stretched, so it has been stretched, and during this process molecule extended and you have cooled. It is not crystallized, but still does not want to go back, cannot go back, because these polar interactions take place and they do not allow the molecules to do exactly what they want to do, but it is still not crystallized. Now, crystallized, you understand that you have molecules that come very close to each other, highly ordered structure, it gives you dimension stability, etc., etc. So, it is possible in the case of acrylic fiber to orient without crystallization, while in the other case just you draw and they start crystallizing, stress induced crystallization. That means you can manipulate this, and so that is what they did. So, they did manipulation and this fiber responded well. So, you could produce a component which has been oriented, not crystalline, a component which has been oriented and heat treated little more so that it crystallized. So, you can produce shrinkable, non-shrinkable component. So, it is called freezing of amorphous orientation. Yeah. So, it is possible to freeze in amorphous orientation. Because it is oriented, therefore, when you give any stimulus, it will like to shrink. Disorientation state, like to go. So, you have an amorphous orientation. In other fibers, it was not possible. You have to do work very hard to reduce crystallization, because naturally they want to crystallize. So, that is why you have in the market commercially successful acrylic high bulk yarns, because you can produce a shrinkable acrylic fiber and a non-shrinkable acrylic fiber. And so, we revise which component is responsible for work development? It is a non-shrinkable component. So, shall we say let us have only non-shrinkable component? So, that is not going to work. So, you got to have both. So, figuratively speaking, it is the non-shrinkable component which is developing bulk, but for doing so you still need a shrinkable component, and the shrinkage difference must be high enough, otherwise you will not see good results. So, now this type of a material is called a biconstituent yarn. So, you need stable fibers. So, it is not like you have a shrinkable filament yarn and a non-shrinkable filament yarn and you say look now come together. It has not worked. So, you need blending and twisting. Okay. And so, it is a staple fiber based thing, all right. So, there is a process called toe to top conversion, but before we do that, you must know how do we normally produce a spun yarn. Let us say polyester, spun yarn, nylon or other synthetic fibers. So, you have to crimp, and crimp is done by stuffer box type of environment. You take a toe, push into a stuffer box where some heating must take place, maybe steam, maybe hot air, and then cut them into staple form. And from the staple, what do? Take a bale, you open the bale, you do the blending if it is required, carding, drafting, sliver, roving, spinning, normal process of making a yarn. And a good amount of these processes are just trying to open fibers and then parallelize them along a desired axis. Lot of work is done. So, one of the things which you do for this whole thing to do, why people wanted to do this process, because you wanted to blend with polyester or wanted to blend with cotton, viscose. So, you needed filament is not likely to give you intimate blends, right. For everything to mix properly, so at a fiber stage you mix them, that is one. So, how do we produce a staple fiber from synthetic fibers? So, you have to cut them. Some of the principles of cutting is called a knife and a bed plate. So, you have a bed plate here. So, this is the plate over which there is a fiber toe is there, maybe spread over a plate, it is being fed, and then this is a system of 4 knives, let us say, very closely they come and cut, for example, and the fiber will keep falling. So, a plate, rotating knives, so you just keep cutting. If you do the alignments properly, then this can happen. Whatever happens is the cutting. The other principles also, So what you do is a knife reel flange. So you have a drum type of thing with the blades like knives are protruding out all over, right? So you can rotate this. So these are knives, sharp knives on a flange arranged in this manner. So there is a blade like going this, you turn this, there is another blade, and there is a gap. So there is a roll and a flange, and so blades, and you have gaps. And so the toe comes, and the toe starts wrapping on a knife reel. So it's getting wound on a roller where the knives are projecting out. Anyone have seen a staple fiber industry? Fiber cutting? So this so-called reel, which has got knives all over which you are making sure that the so-called toe is coming and getting wrapped, and you are putting pressure. So wherever the pressure is high enough, you will start getting fibers coming out. So distance, the staple length, etc., are decided by this so-called roll, and this is a continuous process, and you can suck the thing from inside and take it to the baling press. This is one of the most common type of cutting method is there, which a large number of staple fiber industry will be using. There are others also like an embedded knife. An embedded knife means this is a roll which is a rubber roll. This sheet of yarn or a tow is coming, and then you have another rubber roll which has embedded knives. So the yellow part is a rubber, you can understand. Yellow part is a rubber in which you have the blades just jutting out. So complete support is there of the matrix. So when you compress, it could get compressed. If you put more pressure, then rubber will go, blade will become prominent, right? So this is how you can cut it also. So there are other methods also, principles, but the one which we talked about this is one of the common ones, doesn't require thing. Of course, whenever the blades go wrong, we have to do something about the blades, but it works very well. So you produce a staple yarn and a bale, and then you go for your opening, carding, everything else. So fibers collected and baled. The question people then asked was, why do we need to cut the filament toes the way it is done? That was the question. Because filament toe, the fibers are already parallel. So you are first cutting, then randomizing them, and then say, let's parallelize them again. So that was one of the questions which was there, that something which is already parallel. See, if a cotton, wool, they are naturally grown, they are hardly parallel, so can't do about it, you have to do everything. But why a synthetic material which is anyway being made in a parallel manner, you are first trying to deparallelize and then again opening and spending energy on that. That is why this toe to top conversion systems were designed. So what is a toe? Toe is bundle of filaments. So bundle of filaments is toe, and what is the top?
After cutting the filament,
Yeah.
the short staple fiber is cut top.
The fibers were there also, they were not caught top. So, top is like a sliver. So, cotton people call the same material as sliver, woolen people call the same thing as top. That is one. Acrylic fiber normally follows the woolen system. So, you cut them into staple length which generally higher, having some tendency is replacing wool, is like wool, it is like this thing. So, we are going into those long staple systems also, and because they use the terminology the woolen people are using, wool industry. So, you have top. So, top is like a sliver. So, what you are doing is a toe which is parallel, and then you have to make a top which is parallel. In between you do not need carding, you do not need drafting, you do not need all kinds of things, nothing is required, let us say just do it. So, that is toe to top. In the so called fiber industry, staple fiber industry, after spinning from different spinners, you keep collecting the yarns from different spinners, keep collecting them and make a toe and then crimp and cut. What would be the approximate denier of such a toe? Approximate denier of such a toe. Yeah. Some figures are coming like 3000 denier. Yeah. 2 lakh. Yeah. So, it could be 300,000. So, that is the kind of a toe that you take, because it is a very, very cheap process, right. You want to do mass cutting. So, you take it around, do whatever little stretching you want to do. When you are cutting, just cut them. So, very high denier, so therefore, it becomes cheap. So, that is the kind of thing. But when you are going to convert a toe to top, so it is the sliver denier which will determine what will be the toe denier, right. You can't be making a sliver of a 3000 or 300,000 denier, right. So, this is going to be different from the normal conventional staple fiber industry cutting systems. Advantage is very clear, I believe, that you do not have to spend energy, money in trying to parallelize, and once you have a nice good sliver, then make a yarn, twist and make a yarn out of it. I think we stop here, we will pick up from here.